Welcome to the class on real analysis 2. In the last class, we saw that fx is the indefinite integral of an integrable function f. Then capital F is differentiable almost everywhere and f prime is equal to small f almost everywhere. In this class, we prove that if a function capital Fx is the indefinite integral of an integrable function if and only if capital F is absolutely continuous. The second fundamental theorem states that capital Fx is the indefinite integral of an integrable function over an interval AB if and only if capital F is absolutely continuous. So the theorem states that if fx capital F is the indefinite integral of an integrable function if and only if it is absolutely continuous. So to prove this theorem, we need two lemmas. Lemma 1, let f be an integrable function and capital F be the indefinite integral of the function f. Then this function is absolutely continuous. First, recall the definition of absolute continuity. A real valued function f defined on an interval AB is said to be absolutely continuous if for every epsilon greater than 0 there exists a delta greater than 0 such that for any finite system of disjoint intervals fk, yk, k is equal to 1 to n in AB such that summation k is equal to 1 to n yk minus sk is less than delta, then summation k is equal to 1 to n modulus of f of yk minus f of sk is less than epsilon. And this is the definition of absolute continuity. The proof of the lemma is quite simple. Let epsilon greater than 0 be given. For any finite disjoint collection sk, yk, k is equal to 1 to n in AB, we have summation k is equal to 1 to n modulus of f of yk minus f of sk is equal to summation k is equal to 1 to n. By definition, f of yk is fa plus integral of the function f over the interval a yk minus f of a plus integral of the function f over the interval a sk. That is equal to summation k is equal to 1 to n integral of f over this interval minus integral of f over this interval. By additive property, we can write this term as integral of f over the interval yk sk. But this is less than or equal to summation k is equal to 1 to n integral of mod f over the interval yk sk. Again, by additive property of the integral, we have this integral can be written as integral of mod f over union k is equal to 1 to n sk yk. Take this set as a is equal to union k is equal to 1 to n sk yk. Then this can be written as integral of mod f over a. But by a known theorem, the value of this integral is less than epsilon provided the measure of this set is less than delta for some delta. So if you take a finite collection of disjoint intervals xk, yk, then summation k is equal to 1 to n f of yk minus f of sk is less than epsilon provided measure of a is less than delta for some delta. What is measure of a? Measure of a is equal to measure of, here a is the union of the disjoint intervals sk, yk. And since measure is a countably additive function, and these intervals are pairwise disjoint, measure of this is equal to summation k is equal to 1 to n, summation k is equal to 1 to n yk minus sk. But this measure of a is less than delta, and this means that this summation is less than epsilon whenever summation k is equal to 1 to n yk minus sk is less than delta. This means that the function capital F is absolutely continuous on the interval AB. That is, the function F is in the class AC AB. Lemma 2. Lemma 2 is if F is a function defined from AB to R, and assume that this function is absolutely continuous and its derivative is equal to 0 almost everywhere, then the function f is constant. Let us go to the proof of this theorem, and we will prove that fc is equal to fa for all c in the interval a. That means fx is equal to fa for all x in the interval a. If fx is equal to fa for all x in the interval ab, then f is constant. So we will prove that fc is equal to fa for all c in the interval ab. So consider the set E is equal to AC minus set of all those elements in AC such that f dash x is not equal to 0. Since f dash x is equal to 0 almost everywhere, the measure of this set is equal to 0. Therefore, the measure of the set E is equal to measure of the set AC, but measure of the set AC is the length of the interval, that is C minus A. And let epsilon and eta be arbitrarily small positive numbers. If x is in E, then by definition, look at the description of the set E. The set E is the interval AC minus set of all those elements in AC such that f dash f is not equal to 0. So if you take an element x in E, then the derivative of the function is 0. Recall the definition of the derivative of a function. F dash x is limit h tends to 0 f of x plus h minus fx by h. And f dash x is equal to 0 means we can find a sufficiently small interval x plus h which is contained in AC such that modulus of this quotient is less than eta. That means modulus of f of x plus h minus f of x is less than eta into h. For convenience, take x plus h is equal to y. So for every x in E, we can find a sufficiently small interval x plus h such that this condition is true. If we take an element z in E, then we can find a sufficiently small interval z plus k such that f of z plus k minus fz is less than eta into h. And this is true for every x in E. Now consider the collection of all closed intervals as x varies over E. Then such a collection form a Vitali covering of E. That is the collection of all intervals x plus h, x varies over E is a Vitali covering of E. So then by Vitali covering lemma, we can find a disjoint collection of intervals, finite disjoint collection of intervals sk plus hk, k is equal to 1 to n such that measure of E difference union k is equal to 1 to n, sk yk is less than delta. Here yk is sk plus yk, and this delta is here delta corresponds to epsilon in the definition of absolute continuity of f. Here the function is absolutely continuous, so corresponding to epsilon greater than 0 we can find a delta. So this delta is the delta corresponds to epsilon in the definition of absolute continuity of f. So we have this inequality. So we have a collection of disjoint collection of intervals sk yk a is equal to 1 to n. That is the intervals x1 y1, x2 y2, etc. sk yk. And assume that x1 is less than x2, etc. less than xn. So this is the interval x1 y1. This is the interval AC. Here the first interval is x1 y1. Second interval is x2 y2, etc. interval xn yn. So we have here here y0. This y0 is a is less than x1. Here a is less than x1. x1 is less than y1, less than x2, etc. xn less than yn. And yn is less than c, and c is equal to n plus 1. So we have a chain. If from AC we remove the union of these intervals, that is, from AC we remove the closed intervals xi y. This is the interval AC, and this is x1 y1, x2 y2, etc. xn yn. We remove these intervals from this interval, we obtain y0 x1, y1 x2, y2 s3, etc. Then last yn xn plus 1. So AC minus union of the closed intervals xi y is equal to y0 x1 union, y1 x2 union, etc. yn xn plus 1. Using summation notation, we can we can write this union as summation union k is equal to 0 to n yk sk plus 1. Therefore, the measure of this set is equal to measure of this union. Therefore, measure of this set is equal to measure of this union, and these are pairwise disjoint intervals. Therefore, measure of this is equal to summation k is equal to 0 to 1, and the measure of this interval is its length, that is sk plus 1 minus yk. And look at equation number 2. Equation number 2 is measure of E difference union k is equal to 1 to n, sk yk is less than delta. Here measure of this set, measure of this set is less than delta, and but measure of this set is equal to summation k is equal to 1 to n sk plus 1 minus yk. So by equation 2, this summation is less than epsilon. Again from equation 1, this equation 1, that is for every x in E, we can find a small neighborhood such that f of y minus f of sk is less than eta x. And this inequality is true for every x1, x2, etc. up to xn. So we can write this as, that is equation 1 can be written as summation k is equal to 1 to n f of yk minus f of sk. Here sk yk is an interval, sufficiently small interval which is contained in AC. So this is less than eta into summation k is equal to 1 to n yk minus sk. But this is less than the length of the interval c minus n. So modulus of fc minus fa is equal to, but f of c is f of xn plus 1. Here c is equal to xn plus 1. The point c is xn plus 1. The point c is xn plus 1, and the point a is y0. So we can write modulus of fc minus fa is equal to f of xn plus 1 minus f of y0. But this term can be written as summation k is equal to 0 to n f of sk plus 1 minus f of yk plus summation k is equal to 1 to n f of yk minus f of sk. All other terms will cancel. If we simplify this term, we get f of xn plus 1 minus f of y0. So by triangle inequality, this is less than or equal to summation k is equal to 0 to n modulus of f of sk plus 1 minus f of yk plus summation k is equal to 1 to n f of yk minus f of sk. This first summation is less than epsilon from equation 4 and the second summation is less than eta into c minus a from equation 3. Hence, modulus of fc minus fa is less than epsilon plus eta into c minus a. Here epsilon and eta are arbitrary positive real numbers. Therefore, modulus of fc minus fa is less than or equal to 0. That means fc minus fa is equal to 0. That is fc is equal to fa. fc is equal to fa for all c in the interval ac. That means the function f is constant. Now we are ready to prove the main theorem, that is the second fundamental theorem. The second fundamental theorem states that if capital F is the indefinite integral of an integrable function, if and only if f is absolutely continuous. Capital Fx is the indefinite integral of an integrable function f if and only if capital F is absolutely continuous. So first assume that the function f is the indefinite integral of an integrable function f. So assume that f is the indefinite integral of an integrable function, then by lemma 1 the function f is absolutely continuous. And conversely assume that f be absolutely continuous. If f is absolutely continuous, then f is of bounded variation on the interval a. F is of bounded variation on the interval AB means f can be written as the difference of two monotonic increasing functions. That is, f can be written as some f1 minus f2, where f1 and f2 are monotonic increasing functions. Therefore, f prime is equal to f1 prime minus f2 prime almost everywhere. If a function is monotonic increasing, then it is differentiable almost everywhere. So by Lebesgue differentiation theorem, the function capital F prime is measurable. Moreover, the integral of mod f prime over the interval AB is less than or equal to, here f1 is equal to f1 prime minus f2 prime. Therefore, modulus of this is less than or equal to modulus of f1 prime plus modulus of f2 prime. Therefore, integral of f prime over the interval AB is less than or equal to modulus of f1 prime over the interval AB plus integral of modulus of f2 prime over the interval AB. But here f1 is an increasing function. Therefore, f1 prime is positive. There is no need of the modulus I. So we can write this is equal to integral f1 prime over the interval AB plus f2 prime over the interval AB. But this is equal to f1b minus f1a. But this integral is less than or equal to f2 prime f2b minus f2a. Integral of f prime over ab is fb minus fa. So the integral of f1 prime over ab is less than or equal to f1b minus f1a, and integral of f2 prime over ab is less than or equal to f2b minus f2a. Here the function is here f1 and f2 are monotonic increasing functions. Therefore, f1 and f2 are of bounded variation on the interval ab. That means f1 and f2 are bounded functions. Therefore, this value is finite. That is, the value of the integral modulus of f prime over the interval ab is finite. And this means that modulus of f prime is an integrable function, that means that f prime is an integrable function on the interval AB. So let's assume that dx is the indefinite integral of the integrable function f prime. That is, dx is equal to integral of f prime over the interval ax. Then by lemma 1, the function g is absolutely continuous. Lemma 1 states that if capital Fx is the indefinite integral of an integrable function, then capital Fx is absolutely continuous. Here dx is the indefinite integral of the function f prime. Therefore, the function dx is integrable, is absolutely continuous. The function dx is absolutely continuous. Here g is absolutely continuous and the capital F is absolutely continuous. That is, by right, you are assuming that f is absolutely continuous. So here f is the difference of two absolutely continuous functions. Therefore, small f is absolutely continuous. And since dx is the indefinite integral of an integrable function, so by first fundamental theorem, g prime is equal to f prime. Here g prime is equal to f prime by first fundamental theorem. G is the indefinite integral of the function f prime. So by first fundamental theorem, the function g dash is differentiable almost everywhere. Therefore, g prime is equal to f prime almost everywhere. And since f and g are absolutely continuous, this function f is equal to f minus g is absolutely continuous. Moreover, the derivative of this function f prime is equal to capital F prime minus g prime. But since g prime is equal to f prime almost everywhere, we have f prime is equal to 0 almost everywhere. And that is, f is an absolutely continuous function. Here small f is an absolutely continuous function whose derivative is equal to 0 almost everywhere. So then by lemma 2, the function f is constant. So assume that the function fs is equal to fa for all x belongs to a, for all x belongs to the interval ab. And small f is equal to capital F minus g. Therefore, fa is equal to small capital Fa minus ga. But this is f of a minus gx is integral of f prime over the interval ax. Therefore, ga, the value of the integral ga is equal to 0. So small fx is equal to capital Fa. For equality, we can write small fx is capital F minus dx. Capital Fx minus dx is equal to capital Fa. From this equation, we can write fx is equal to Fa plus integral of f prime over the interval ax. That is, capital Fx is the indefinite integral of the integrable function f prime. So if capital F is absolutely continuous, then capital F is the indefinite integral of an integrable function f prime. And this completes the proof of the second fundamental theorem. So the second fundamental theorem is, if a function capital Fx is the indefinite integral of an integrable function, if and only if f is absolutely continuous. So define a function f from 0 1 to r by fx is equal to x into sin 1 by x if x in 0 1 and 0 if x is equal to 0. The question is, does there exist an integrable function g such that x sin x is equal to integral of g over ax, or is x sin x is the indefinite integral of some integrable function g? But second fundamental theorem states that f is an indefinite integral of an integrable function if and only if f is absolutely continuous. So this is true if and only if this function is absolutely continuous, that is x into sin x is absolutely continuous. First we show that this function is of bounded variation on the interval a. So consider a partition p is equal to 0 2 divided by 4n plus 1 into pi, 2 divided by 4n pi, 2 divided by 4n minus 1 into pi, etc. 2 divided by 2 pi, 2 divided by pi 1. And this is a partition of the interval 0, 1. So the variation of the function indicates the subinterval, that is f of sk minus f of sk minus 1. When a function fx is x into sine 1 by x. So this is sk into sine 1 by sk minus sk minus 1 into sine 1 by sk minus 1. But sk is the point 2 divided by 4k pi into sine 4k pi by 2 minus sk minus 1 that is 2 by 4k minus 1 pi into sine of 4k minus 1 into pi by 2. But value of sine function, sine 2 pi k is 0. The first term will vanish, and second, this term is always minus 1. So we get this is 4 by 4k minus 1 into pi. Therefore, summation k is equal to 1 to n modulus of f of sk minus f of sk minus 1 is equal to summation k is equal to 1 to n 4 divided by 4k minus 1. But this tends to infinity as n tends to infinity. And this means that the function f is not of bounded variation on the interval ab. But we know that AC01 means the class of all absolutely continuous functions on the interval 0, 1 is a subclass of this class. Therefore, this function is not in the class AC01. That means the function is not absolutely continuous on the interval 0, 1. So, this is not possible. Thus, this representation is not possible. Now, consider another example. Is the function fx is equal to sin x, x in 0 to pi is of bounded variation on the interval 0 to pi. And note that cos x is an integrable function, and sin x is the indefinite integral of the function cos x. So this is sin x is the indefinite integral of cos x. But by second fundamental theorem of Lebesgue integration, the indefinite integral is absolutely continuous. That is, the function sin x is absolutely continuous. And this means that the function sin x is of bounded variation on the interval 0 to pi. Then what is the total variation of this function? But total variation of this function, also note that the function cos x is a C1 function. Therefore, the total variation of the function is equal to integral of mod f prime over the interval 0 to pi. But f prime is cos x. Therefore, this is integral of mod cos x over the interval 0 to pi. And note that the function cos x is positive in the interval 0 pi by 2 and negative in the interval pi by 2 3 pi by 2 and again positive on the interval 3 pi by 2 2 pi. Therefore, this integral can be written as, in this case, here the Lebesgue integral, this Lebesgue integral is same as the Riemann integral, the function is continuous. Therefore, this integral can be written as integral of cos x over 0 pi by 2 and minus in the interval pi by 2 3 pi by 2 cos x is negative, so minus integral of cos x over the interval pi by 2 3 pi by 2 plus integral of cos x over the interval 3 pi by 2 2 pi. We compute this integral, we get the value 4. Let us stop here. In the next class, we will discuss abstract measure space.